Hello everyone, welcome back. So now we do section 4.3, the new idea. To define the stochastic integral for anticipating integrand. Recall from the previous video we have the equality. We have these two equality. The first one, let me put this as 1 here and this as 2. The first one is regarding B1 as independent of T and then pull it out so we get B1 squared. The second one is in order to be consistent with the double Ito-Wiener integral. And the question, which one is more reasonable? Of course, this is all depends on what we want. If we want to be, if we want to have the new stochastic integral being consistent with the Wiener-Ito double integral, then 2 would be more desirable. And so how can we define this integral from 0 to 1 and B1 dvt to be B1 squared minus 1? So the idea, this is a new idea. The new idea actually comes from Ito himself in his 1976 Kyoto Symposium, namely reverse Ito's idea. Namely 1. We keep the Brownian motion. And the filtration. The filtration is the one given by the Brownian motion. So we keep the Brownian motion and we keep the filtration. Now you see in Ito's idea, he kept the integrand B1, but we keep the Brownian motion and the filtration 2. We decompose the integrand B1 as follows. Write B1 as BT plus B1 minus BT. So we decompose B1 into the sum of 2 stochastic processes. The first one is BT. The second one is B1 minus BT. So we have decomposed, which is very simple, which decompose B1 into the sum of BT plus B1 minus BT. Of course, this BT cancels out, it's B1. And then observe these 2 terms. The first term, AT, is adopted with respect to this filtration which we keep. And the second term has some special property. I observe that this second term has a very special property, namely being independent of ft for each t. It has this very special property. In the next section, we will make the abstract version of all this concept. At the moment, you see I'm using this integral as a motivating example to introduce or to discover several new concepts and new ideas. Okay, so we have decompose this integrand B1 into the sum of two stochastic processes, one being adapted and the second one being independent of ft for each t. And then the next one is a crucial idea in this new theory of stochastic integration. And the idea is this, very interesting. For the evaluation of the integrand, and therefore the integrand is B1. For the evaluation of the integrand, we use the depth endpoint. The depth endpoints of subinterval. For the for the adapted part, so in this example is for BT. So the evaluation for this for the integrand, we use the left endpoint of the subinterval for the adapted part. This in order to be for the new integral consistent with the Ito theory. But now the critical idea here, we use the right endpoint or subinterval. Of subinterval for the other part for B1 minus BT. That's it. And that is the crucial ideas. Okay, we turn to the next page. Okay, page 11. Here we go. Then the integral from 0 to 1 of b1 dbt is the integral from 0 to 1 bt plus b1 minus bt dbt. And that equals to the limit as n goes to infinity of the sum I from 1 to n, the partition. The sum I from 1 to n of, now for the, this is the adaptive part, and this has some special property, namely independent of ft. And for the adaptive part, we evaluated it at the left end point, namely t sub I minus 1. And then for the second term, we evaluate it at the right end point. And then Brownian motion increment. So you see, the crucial thing is the evaluation point. Oh, maybe I should put parentheses here to put this as second term. Okay, so this is the limit as n goes to infinity, summation I from 1 to n. Then we rearrange the value of the integrand. Okay, so the first time I put this as b1, and then minus bt sub I minus b of t sub I minus 1. And the Brownian motion increment. Now, inside the parentheses, we have the difference, the first term and the second term. If we cover the second term and multiply b1 to the Brownian motion increment here, then we get b1 times the sum of the Brownian motion increment is b1 times b1. And then minus the limit as n goes to infinity of the sum I from 1 to n. And here, this is the Brownian motion increment, so we have the Brownian motion increment square. And now, the limit of this is exactly the causative variation of the Brownian motion on the interval from 0 to 1. And so this equals b1 squared minus the causative variation of the Brownian motion on the interval 0 to 1 is 1. And so you see, we get this value. Hence, the integral from 0 to 1, b1 dbt equals to b1. So this is our new integral, or new stochastic integral. And for this new stochastic integral, the value is consistent with the double Ito-Wiener integral. Okay, so we stop here for this video, and we'll continue in a second.